Good morning, everybody. Welcome to Cold Monday morning of Chem 1211 with your host, me, Dr. White. Hi. Hi. Couple things. First of all, over the last couple days, I had some personal stuff that popped up along with a quiz in this class labs. This class tests my other class, the other school labs there. And I forgot to post the calculations for the airbag lab. Bad, Dr. White. Bad, Dr. White. The double bad, Dr. White. I apologize. What I've done is I've extended the deadline for the airbag lab by 1 week. Later today by 8 p.m., I've already got it written out this way. I got to make it pretty so I can post it. I'll post the step-by-step calculations, and you'll have an extra week to do that if you haven't. If you've uploaded a lab and there's some mistakes in your calc, I'll be nice when I grade it. That's my mistake, not yours. So, anyways, that takes care of that. Another important thing today, right after I'm through talking about important things, I will be going through quiz 4. And thank you, thank you, thank you. Everybody did real good on quiz 4, but I expected that. Yep. Know why? Because when I've taught Chem 1211 before, a number of times, quiz 3 and 4 make up my test 3 when I'm giving tests. But as you know, this semester, tea break time, I need it. I did. This semester, I can only give 2 tests and the rest have to be quizzes. So quiz 3 and 4 were broken up from test number 3 when I do it face to face. But overall, everybody did good, which is a good thing. Keep up the good work. All right. One other thing, this Wednesday, I will have a very special announcement, 10-point announcement. Yep, 10-point announcement. So be sure also I'll post it on Blackboard by Wednesday morning. Keep an eye out for this special announcement I'll make Wednesday morning. And with that, I'm going to get going. And with that, I'm done with quiz number 4. Before I move on, something important. Do you have any questions? I'll look down at the chat too. Clean off whatever this white stuff is. I'm white stuff too. All right. Now I would have a question. We've had 4 quizzes, 1 test, and a lot of labs. What's my grade right now? Well, that's a good question. Let's take a look at that. There are 2 methods. Method 1. All right, method 1, you add up the points for your 4 quizzes add up test number 1 score and divide it by 3. If that number is 90 and above, you're getting an A, 80, 89 B, 70, 79 C, 60, 69 D, below 60 F. Method number 2. Method number 2, remember, you can either drop test 1 or 2 quizzes. And method 2, we drop test 1 and take the sum of your 4 quizzes and divide that by 2, and you'll get a number Y. If Y is 90 and above, it's an A. If it's 80, 89, B. 70 to 79, C. And 2 more. And 59 or lower F. And there's a third method. And the third method, Z is equal to the sum of the 2 highest quizzes plus test number 1 divided by 2. And if Z is 90 and above, it's an A, 80 to 89 B, and 70, 79 C, 60, 69 D, 59 or lower F. So one thing I should point out, and somebody has, all right, Anna, I'll answer your question in a second, maybe more than a second, when I'm done with this. Now, this assumes you've handed in all the labs. If you've handed in the labs, if you've noticed by now, I'm not a tough grader. How many points can I take off? Labs usually keep your grade the same or raise it a little if you've handed in all the labs. And method 1, 2, and 3 assumes that. Otherwise, it gets real complicated. Now, most of you, based on test 1 performance, not all, but most of you will probably at this point use method 2 to determine your current grade, which if I remember looking at the grade book, most of you are doing pretty good, assuming you've handed in the labs. Before I answer Anna's question, do anybody have any questions on method 1, 2, or 3? All right. Now, Anna asked how many tests are left. Well, let's go through the whole thing. There's 2 more quizzes, 5 and 6. There's test number 2, which will be after quizzes 5 and 6. It'll be the very last week of the semester. Plus, there'll be a final exam, which is a departmental required American Chemical Society final. For Chem 1211, there's a certain ACS, American Chemical Society final. So we still got, you still have, let's see, 2 quizzes, that's 200, a test, 100, 200, and the final 15. So there's still, out of what is it, 500 or 600 points, I forgot right now. I had to change it. Normally it's because of the way I did quizzes. But anyways, there's still a lot of points left to go. And if you're having problems, come to my office hours, Tuesday and Wednesday night from 7 to 7, 6 to 7:15. If you cannot make it to my office hours because you're working, let me know and I'll find a way to arrange a Zoom meeting to help you out. The question is, if you do bad on the vinyl, it won't count. It will count. I'm required to do that. But I made the final worth only 15 points. Normally, when I give my own final, it's worth about 200 points. Relax, but yeah, it's worth a lot more. So because of the way with the pandemic and everything, I had to juggle things around. And I like my special effects. So any other questions about what's coming up? Because we're really only got a couple more weeks this semester. It's almost Thanksgiving. Where does the semester go? Any other questions? Going once? Going twice? Oh, I forgot to look at chat. Nope, I got everybody's question. So the final will count a small amount, but that small amount might make the difference between an A and a B or a C and a B. So it behooves you, ooh, fancy word today, it's important that you do good on the final. And the last week of the semester, I'll be doing a whole semester review, which is also why students do good on my last test and the final exam. All right, any other questions? Well, let's move on. All right, Zoom told me, but I'm still going to use my thumbs up, people. Everybody see I'm using my North Side Chicago accent, the Chattelier's principle on your screen. Oh, thank you, Brianna. All right. Now, I will never, ever ask on a test, or the ACS doesn't either, but what is Le Chatelier's principle? But you'll need to know how to use it. All right, what is Le Chatelier's principle? Le Chatelier is a great French chemist. You know something I've never done? And for those who came in late, I'm postponing the airbag lab due date by 1 week. It's not due tomorrow. It's due next week because I'll post by 8 p.m. today. Personal things got in the way, and I forgot, bad Dr. White, to post the calculations, but I'll do that by this evening. So it's due not tomorrow, next week. But where was I going? Oh, he lived in 1800s, early 1900s, French chemist. and he worked with equilibrium. Wow. He published it in late 1884 through 1914. And this is considered one of the key principle in chemical equilibrium. All right, let's look at this. When a chemical system at equilibrium is disturbed, otherwise known as stress, the system shifts in a direction that minimizes that disturbance. Another way of saying it is if a stress, a changing condition like temperature or concentration, is applied to a system in equilibrium, the system will readjust, change the position of the equilibrium in the direction that best reduces the stress imposed on it. Now, if you're at a party and some really obnoxious person is doing this to you, hey, look, remember this, you're going to say, stop that, or you're going to walk away from that. And that's the sort of example of the Chatelier's principle. When you're under stress, you're going to do things to minimize the stress. Well, how can a chemical equilibrium do that? Good question. Thank you, Dr. White. You're welcome. All right, let me remind you that at equilibrium, does everybody see the following reaction right here on your test? Thank you, Gianna. All right, now what this means is at equilibrium. How do you know it's equilibrium? Double-headed arrows. The concentration of A, B, C, and D are going to be fixed in order for this to be true. So at equilibrium, there's a certain amount of A, certain amount of B, certain amount of C, certain amount of D. And that's a chemical equilibrium. Now, the Chatelier's principle occurs when you put a stress on that equilibrium. And how do we do that? Well, we change the concentration of A, B, or C, or D. Let's take a look. All right, everybody see A plus D, equilibrium, C plus D. Thank you, John, again. All right, now, something I need to teach you. When this reaction occurs, when A and B react, oh, by the way, I forgot to do some things. It's Subtle Monday. Subtle. Can't know this. All right, when A and B react, the concentration bracket A, close bracket, means concentration decreases. Concentration of A and the concentration of B decrease. It gets lower. It's consumed. They react together to make C and D. Now, this is a concept students have trouble with. And let's assume, well, I shouldn't do this, but You had your favorite cookie in your hand. One of my favorite are the ones you get at good delis and good bakeries. You know, the smile cookies with the butter cookie with the glaze. Oh, I'm getting hungry now. But anyways, you have one of those smile cookies and you eat half of it. Do you have the same amount of cookie in your hand or less? And the answer is less. It's decreased because you ate some of it. It's been consumed. So when something reacts, is consumed, how do you like my special effects today? Oh, I'm going all out. Anyways, when it's consumed, you have less. Now, when A and B, and what we're talking about, if the reaction goes in this direction, A and B react, they make more C and D. And when you make more of something, the concentration of C, the concentration of D will increase. So when you make something, in this case, when A and B react to make C and D, you're making more C and D if the equilibrium is shifting to the right. And when you make more of something, the amount, the concentration, bracket C, close bracket, means concentration, which is a measure of amount, increase. It gets higher and it's produced. Now, for whatever reason, students have a lot of trouble understanding this. So let's repeat. When two things are reacted, A and B, when you consume them, the amount of A and the amount of B decreases. Oh, it's time to get you hungry again. If you have a bag of, this is the most dangerous thing food-wise for me, a bag of Lay's sour cream and onion potato chips, and you open it up and you eat half the bag, how much do you have in the bag? More or less? And the answer is less. By the way, in my house, you open one of those big bags. I don't know why, but they evaporate and disappear like that. I have yet to have one of those big bags last more than overnight. Never. They just disappear. They're consumed. So when you react something, just like the potato chips, when you consume it, boy, this is a high calorie lecture today. But anyways, you have less of them. Now, if somebody gives you some money, that would be nice, and says, here, hold on, what do I got? Ooh, one of my keepsakes. Can everybody see this? This is a currency that no longer exists. It's 2.5 guilders, which is the Netherlands. I worked there a lot, and it's one of my mementos. But if I give you 2.5 guilders, are you going to have more or less money? Well, you're going to have more. So when you produce something, make something, obtain something, you're going to have more. When we're talking about concentration, the concentration goes up. So how do we put this all together with Le Chatelier's principle? I will warn you, take a deep breath, let it out, take a deep breath, let it out, relax. This is one of the more challenging concepts for students this semester. Take a deep breath, let it out. All right, for this equilibrium, .4 points each. For this equilibrium, you're always going to be given a chemical equilibrium. For A plus B is an equilibrium, and that's what the double-headed arrows mean, plus C plus D. What happens to the concentration of A and D, B and D if I add more A? Well, how do you know what to do? You use the Chatelier's principle. A system under stress shifts in the direction of the shifts to the direction that relieves the stress of the system. Well, what's the stress of the system? At equilibrium, I had a certain amount of A. Now I've added more A. How do you do that? You have this in a beaker, take a test tube of A, eyedropper, and put some drops of A in there. And you've now put a stress. Because at equilibrium, there should be a certain amount of concentration of A, B, C, and D. So it equals the equilibrium constant. Well, now, oh no, there's too much A. How do I get rid of A? Well, the only way you can lower the concentration of A, why? Because the stress is too high, because you've added it, is A and B react to make more C and D. When A reacts with B, it's consumed. And when A reacts with B, when it's consumed, the concentration of A will get lower. Well, that happens, B reacts, and B will also get lower. So, first of all, the concentration of B decreases. Or if you're lazy, organic chemistry, put an arrow down, decreases. Or you could have said gets lower. Now, in order to lower the concentration of A and B react, and they make what? More C and more D. When you make more of something, what happens to the concentration of that chemical? Make C and D, the concentration of C and D increase, gets higher because it's produced. So therefore, D will increase, or you could have put an arrow up, or you could have written gets higher. And that's Le Chatelier's principle. There was, when we added more A, the concentration of A was too high and it was under stress. Oh, I'm under stress. And you didn't know it. Molecules could get stressed. They can, sort of, maybe. And now, in order to get rid of the excess A reacts with B to make more C and D. When something reacts, it's consumed. There's less, the amount decreases, it gets lower. And therefore, since B is reacting with A, the concentration of B also will decrease. Now, when A and B react, what do? the equilibrium is called shifted this way, makes more C and D. And when you make more of something, the amount you have is greater. Therefore, the concentration, remember bracket, chemical formula, close bracket, is concentration. That means moles per liter. And that means how much there is of something. And since you're making more D, the amount you'll have increases. Or if you're lazy like I am, you could put an arrow up, or you could write gets higher. And that's Le Chatelier's principle. And good news, tomorrow's lab, you're going to have fun stressing equilibrium. It's a lot of fun, but I'm a chemist. I'm an organic chemist, but just being a chemist, doing Le Chatelier's principle experiments are fun. Speaking about fun, it's time to take a 5-minute break. I'm going to take a 5-minute break. I'll see you in 5 minutes. I'm back. For those of you who came in late, two things. One, I'll cut out the answers for the quiz 4, but come to my office hour. If you can't come to my office hour, email me and I'll set up a Zoom time to help you out. The other thing, due to bad Dr. White, I, for personal reasons, forgot about the calculations for the airbag lab. I will post them, send them out also in an email, by 8 p.m. today. And therefore, the airbag lab, which would have been due tomorrow, I'm going to give you an extra week. And hopefully that will help you out. All right, let's get back to the Chatelier's principle. And remember, a system under stress shifts in the direction to remove that stress. And when things react, their concentration decrease. When things are consumed, react, you have less. When things are made, produced, you get more. So once again, when you make something, the concentration will increase. When you react something, it's consumed, used up, the amount, the concentration decreases. So let's look at this problem, 4 points each, and let's look at B. All right, we have this chemical equilibrium, and the question is B. What happens to the concentration of B and D if I add more C? And now if we look at that, what's the stress? At equilibrium, there was a certain amount of A, certain amount of B, certain amount of C, and a certain amount of D. That's the concentration that equals to the equilibrium constant KEQ. Now, we've added more C, so now the equilibrium says, oh no. I don't know if it goes like this, but it goes, oh no, I'm under stress. We have too much C. Why? Because we added more. So the stress is, oh, too much C. How do we get rid of excess C? Well, the only way you can get rid of it is having C react with D. Remember, this is an equilibrium. It can go both directions. And if C reacts with D, C is consumed. When something is consumed, the concentration decreases. So if C reacts with D, and it's called to shift the equilibrium in this direction to the left, then what happens to the concentration of D? Well, D reacts, and it's reacting with C to get the level of C lower. And therefore, if something reacts, it's consumed, and the amount decreases. And you can put an arrow goes down, or you could write gets lower. Now, in this reaction now, to get rid of the excess C, C and D react to make more A and B. When you make more of something, what happens to the amount the concentration. Well, when you make more, like in this case, I have C and D, but anything, you'll have more. The amount increases. So therefore, since we're making more A and B to reduce the stress of too much C, we make more B. When you make more B, guess what? The amount increases. You can put it increases, increase or increases, put an arrow up, or you can say it gets higher. And again, that's Le Chatelier's principle. It's my North Side Chicago accent, French accent, and was system shifts in the direction to lower the stress. And at equilibrium, there's a certain amount of A, B, C, and D. Let's everybody take a deep breath, let it out. Take a deep breath, close your eyes and relax. Let it out. This is not easy. It takes a while. It took me a while for my brain to wrap around what's going on. All right, let's continue on with the same reaction. Remember, the double-headed arrows means equilibrium. That's two opposing reactions. A and B can make C and D. At the same time, C and D can make A and D. Remember, bracket, chemical structure or formula, closed bracket, is concentration amount. All right, everybody see what happens to the concentration, bracket B, closed bracket. Thank you, Gianna. And concentration of B and D if I remove some C. And so at equilibrium, there was a certain amount of A, certain amount of B, certain amount of C, and a certain amount of D. Now I've removed some A. And oh no, there should be a certain amount of, remove some C. I said A, meant remove some C. At equilibrium, there should be a certain amount of C. Now there's less. Oh, I'm under stress. Oh no, what do I do? Well, I need to make more C because I've removed some of it. How do I make more C? A and B react to make more C and D. Now, when something reacts, it's consumed. The amount gets lower. So therefore, if A and B are going to react to make more C and at the same time more D to remove the stress, because I removed some of the C, bad Dr. White. But anyways, that means B will be consumed and the concentration decreases, will decrease. If you want, you could put gets an arrow down, or you could write down gets lower. And since we're making more C to remove the stress, that I remove some C will make also more D. And when you make more of something, the concentration, the amount increases. It gets higher. and it gets higher. Now, this is the Chattelier's principle. And one of the questions you should always have in my classes, why am I learning this stuff? Well, the obvious reason is someone said you have to take this course, come 12, 11, to get into A, another course as a prerequisite, or B, because your major, you need this chemistry course, or you need it to get into a program like nursing. But really, why should you learn this? Well, it turns out in your lungs, and I forgot either your kidneys or your liver, the Chatelier's principle is used in your lungs to remove and inhale, get oxygen into your body, exhale. The Chattelier's principle helps get the carbon dioxide out of your body. And if you don't think that's important, well, it is, because that keeps us alive. I should warn you, the last biology I had was freshman year high school, not because there's anything wrong with biology, but by then I knew I was going to be a chemist, and I did become one. All right, but why else? Well, in real life, in the chemical industry, we use Le Chatelier's principle all the time. An example I have done, and I won't do the whole chemical reaction, a certain reaction I did when I was at Borden Chemical. You reacted two chemicals, actually phenol and formaldehyde, A and B, to make a molecule C, a resin that's used as a glue to hold sand together to make the molds for car engines. Ooh, show and tell time. Everybody see this in front of their screen? This black, and we call it a dog bone. This is made with a resin I invented using Le Chatelier's principle. If you notice, the sand is pretty good. This is made so you put it in a machine called an instron and pull it apart and see how much force it takes. And it's an important measurement. But they make these dog bones. I had this made, or I saved it. Actually, I've got fancy. I put a couple of jewels in there too, because it's my resin that I created. I got a patent for it. But to make the resin that holds the sand together for this dog bone, or to make your mold to make car engines, or how many of you have ever seen a manhole cover in the street? Big metal thing. Those are made in foundries and molds of sand and resin. And the reaction to make that resin C is an equilibrium reaction, and it's very slow. To speed it up, when you're making the reaction, you remove the water. And by doing that, remember Le Chatelier's principle, equilibrium under stress shifts in the direction of the equilibrium to remove that stress. Well, if I'm removing the water while the reaction is going, it's going to keep on saying, oh no, there's not enough water. I have to make more water. Therefore, A and B react to make more C and water. And by doing that, I'm shifting the reaction and I make it go to completion by removing water. I don't know if I mentioned this. I should. I'll do it again later in the semester. Everybody see like where it says Wabash National, the truck with the cylinder behind it on your screen? Thank you, Brianna. And that's called a tank wagon. Tank wagon here, they call it chemical tanker trailer. Now they're called tank wagons. And these tank wagons are standardized. They're 40,000 pounds, 8,000 gallons. No, 5,000 gallons. It's been a while. 5,000 gallons, 40,000 pounds. And I've done reactions where the amount of chemical in we call it a reactor, like you would call a beaker, but this is much more. And I'll later in the semester, I'll have a real surprise for you, a tour of a chemical plant. But anyways, I've run reactions using Le Chatelier's principle, where we use the amount of chemicals you start with, fill 4.5 of those, and that's a lot of chemical, but it works. And we take off about 6,000 pounds, a couple thousand gallons of water, but the reaction takes 34 hours. If you didn't use Le Chatelier's principle, it'd take months, maybe longer to finish. But Le Chatelier's principle, by pulling off something to shift the equilibrium in the direction you want, will make it go quicker. So that's an important part of Le Chatelier's principle in the chemical industry. All right, guess what? I haven't been sharing. And here's one for you. Here's an equilibrium. A plus B is an equilibrium. Double-headed arrow tells us that. Let me fix up this arrow. Double-headed arrow. And what happens to the concentration of B and D if I remove some A? Your turn to have fun with Le Chatelier's principle. And when you're done, give me a thumbs up. And the answer is either increases or decreases. And please don't take a coin and go, heads it's increased, tails it's decreased. That doesn't work. Oh, Dr. White made a funny. Not that funny. And when you're done, give me a thumbs up. I was looking for something I might have missed if you did a thumbs up. All right, I found a reaction. Give me a thumbs up again if you're done. All right, my turn. What happens to the concentration of B and D? We're talking about this chemical reaction if I remove some A. Well, at equilibrium, there was a certain amount of A, B, C, and D, the concentration. Now I've removed some A. So the stress is, oh no, it doesn't really do that, but it gets the point across. There's not enough A. Some has been removed. I need to make more A. How do I make more A? I shift the equilibrium in that direction. I react C plus D to make more A and make more D. Now C and D react. When something reacts, it's consumed. When it's consumed, like eating the cookie, you have less. The amount decreases. You can show it by an arrow, or you can also say gets lower. Now, since C and D are making more A, because it's to replace what was removed, you also make more B. And when you make more of something, you have more of it. Profound, but true. And therefore, the amount is more, the concentration will increase. And you can write it as an arrow up, or you can also say gets higher. And that's legit. Oh, let's do another one, but let's do something with chemicals. All right, here's a chemical equilibrium. PCl5, Cl5, phosphorus pentachloride is in equilibrium with phosphorus trichloride plus chlorine gas. And all right, what happens to the concentration of PC5, phosphorus pentachloride, and Cl2, chlorine gas, if I add more phosphorus pentachloride, PCl3? Your turn. And you got two choices. Either goes up, increases, goes down, or you can call it decreases. And when you're done, give me a thumbs up or any other emoji you want to use. Did I have one that's a thumbs down? I think recently they added that. And you can use the smiley face or any other emoji. I'd still like to change the name to Symboli. I remember it takes a while to master this, but there'll be at least on quiz 5, at least 12 points of these type of questions, maybe more. Thank you, Brianna. Thank you, Gianna. Let's give Anna a little more time. And remember, I haven't said this in a long time. Thank you, Anna. I haven't said this in a long time, but I think I can go face to face right now. Remember, in my class, there's no such thing as a dumb question. In my world, there's no such thing as a dumb question. Always, always feel free to ask questions. Now, I'm still trying to figure out what's the meaning of life, but in terms of chemistry stuff, I know a lot. Do I know everything? No, even in chemistry. All right, let's get to work. For this equilibrium, at equilibrium, there's a certain amount of phosphorus pentachloride, phosphorus trichloride, and chlorine gas. I've added more phosphorus trichloride, this. And at equilibrium, there was a certain amount. Now there's too much. And the equilibrium goes, oh no, we've got, it really doesn't do that, but it gets the point across. We've got too much PCl3. How do we get rid of some of that? Well, when something reacts, it's consumed and the amount goes down. I like those special effects. Therefore, the equilibrium needs to shift in this way, because by shifting in this way, reacting PCl3 with chlorine, you will lower the amount of PCl3. Well, if chlorine reacts with the PCl3, guess what? When something reacts, the amount you have is consumed, and when something is consumed, the amount you have decreases. Just like when you eat a cookie in your hand, after you take a bite, you'll have less cookie in your hand. And you could also put an arrow down, or you could write gets lower. Now, since PCl3 is reacting with Cl2, it makes more PCl5. And when you make more of something, what happens? The concentration, how much you have, the amount you have, increases. Which means you could do an arrow up or it gets higher. And this happens, it follows what we call the Chatelier's principle. It happens. And tomorrow you'll be doing a lab where by adding or doing other things to a reaction in a test tube, you can watch changes happen. Now let's see something if I can find it real quick. All right. Everybody see the Chattelier's principle YouTube on your screen?
In this lab, we will be studying a chemical reaction at equilibrium between two complex ion formations of cobalt. Because they form complex ions with water and or chloride ions very favorably, we can see which side of the reaction is favored by the color changes due to crystal field theory, which is not part of this lab. But we're going to be studying with Chatelier's principle and noticing at equilibrium, if a stress is made, let's say a stress is made that forces the reaction to go.
All right, right here, this guy's using a double-headed arrow to show equilibrium. I don't like that, but I'd make this video. But this cobalt hexahydrate reacts with chlorine ions to form cobalt hexa or pentatetrachloride and water. The cobalt H2O6 is red. The cobalt COCl4 is blue.
Thermodynamically to the right, we should be able to see a nice blue color because the reactants get used up and we'll make more products, which will be, of course, that complex with the chloride ion with that ligand. And of course, back at equilibrium, if we do something that favors the reverse reaction, where we're going to make more of the red by using up the reactants, and we will make more of the cobalt complex that has the water surrounding it as the ligand, which will be red, we can observe these shifts in equilibrium. So let's get started. So just to show you, this is the color or baseline colors of the cobalt complex with water. And this is the color, a nice blue color, of the cobalt complex with the chloride ion. So clearly you can see who's favored and by looking at these colors. And this is, I believe, a purple color, although I have a difficult time with colors, of the equilibrium mixture of both. All right, so we're going to put out some test tubes here, and we're going to follow our procedure as follows. So here's our 4 test tubes. And again, right now we see the pink color, so all these test tubes currently have a lot more of the reactants and products, as by the pink color favoring the copper complex with water. So we're going to begin our first test, and we're going to just add some hydrochloric acid into the first test tube.
Which is adding Cl-1. Watch what happens.
See that thermodynamically, there is a shift from this reaction going to the side with the both.
All right, you look here, he had this red stuff, he added more Cl-, and it's going to shift this way to reduce the amount of Cl-. It makes COCl4, and that's the color change you saw. And here, by adding it,
there is a shift from this reaction going to the side with the blue compound. So now we're making a lot more cobalt chloride complex, the complex that is blue. Okay, and very clearly, you should be able to figure out in your lab who is being used up and who is being increased. All right, so in test tube 2, we're going to add some calcium chloride. And we'll add some more. And you should be looking at the bottom of the test tube. And the calcium chloride is going to dissociate into its ion. That's important you understand. So the calcium +2 and then
Once again, calcium chloride is adding more Cl minus. It has too much. It reacts with the COH2O6 to make more of the blue COCl4, and that's why at the bottom it's turning blue. Which
meaning you see a shift toward the blue side. We are making a lot more of that cobalt ion complex with the chloride ion. People know which side we're shifting, and all right, so here comes test tube 1 again, which we can see is clearly favored, all right, with the blue compound. All right, and now we're going to add some water.
All right, now if you look at the equilibrium, can everybody see this on their screen? Thank you, Gianna. All right, now in test tube 1, there's an equilibrium where the predominant species is the blue COCl4. There's a certain amount of water, certain amount of COCl4, certain amount of Cl minus, and certain amount of COH2O6, the cobalt hexahydrate called. And now by adding more water, there's too much water. And how can you get rid of the excess water? Water reacts with the blue cobalt tetrachloride to make more Cl minus. It shifts this way, and more of the COH2O6, the cobalt hexahydrate, which means when he adds water, if Chatelier's principle really works, it should turn, test tube 1 should turn reddish color. Let's see if that happens. Oh, the suspense is killing me. Not really.
Right, so now adding some Poland spring water, and again, this is not they didn't pay us anyone to do this, but we're going to add some water. And by adding water, you can see definitely a shift toward the pink cobalt complex. And that pink cobalt complex is on the reactant side. So again, you should be able to figure out where the reaction is shifting to by what.
This is a good one. I'm going to save it. All right, that's really how quickly the Chatellier's principle works in certain reactions, and it works quite well. Now, let's move on. Let's look at, and this is a little different, but I'll go through it, the effect of a change in temperature on the equilibrium for exothermic reactions and endothermic reactions. Now, I have to do a little background information. All right, now let's look at an exothermic reaction. And you learned about the energy diagram. And what this means is if I have a reaction A plus B in equilibrium with C plus D, because it's exothermic, it gives off heat. On the right, we have heat. So this is the exothermic reaction equilibrium we're going to be looking at. But first, let's answer the question, how do you change the temperature of a reaction of like A plus B is in equilibrium with C plus D plus heat? Well, there are two ways. One, one is put the reaction in a beaker of ice water. Ice, I hope you all know, is cold. What does it mean when something's cold? It's removing heat from you or whatever. So the important thing, when you put a reaction in a beaker of ice water, what does it do? Putting something, making it colder, putting it in an ice bath, otherwise known as ice and water, removes heat. If you're real hot in the summer and you take an ice bag and put it on your forehead, that will cool your forehead and your body down. Or if you get in a bathtub of ice water, ooh, that would be cold. But anyways, that will remove it. In fact, that reminded me of something. Dr. White's story. Do I have time? I do. When I was about 5 months old, I was told this, I don't remember it. Back when I was a baby, they gave all babies what's called smallpox vaccination. And that's to protect you from smallpox. And what they do is they inject you with similar called cowpox to bring up your immunity to smallpox. Well, guess what? I almost died from that. I came down with cowpox and how that happened. And at one point, my temperature in my body was so high that they put me in an ice bath, a bath with water and ice to keep my body temperature down so I didn't die. By the way, surprise, surprise, I didn't. Yay. But that's because it removed the heat from my body so it wouldn't kill me. So an ice bath, ice and water, removes heat. And you should know this. Ooh, subtle time. All right, so put a reaction by decreasing the reaction temperature. This decreases when you decrease the reaction temperature by putting it in ice water or ice bath, you should know that removes heat. Now, the opposite of that is put a reaction you put the reaction in a beaker of boiling water, you should know that increases the heat what you're doing is adding it's not what I want to write. Well, you're adding heat by increasing the reaction temperature. And so there's two things you should know. One, when you put a reaction in a beaker of water, ice water, you're removing heat. The cold takes the heat out from a reaction. You decrease the reaction temperature. When you put a beaker in a put a reaction in a beaker of boiling water, which is hot water, I'm about to sneeze. Excuse me. You increase the heat. You add heat. And this we use with Le Chatelier's principle. So, how are we doing on time? You know something? Let me go through this again. When you have either endothermic or exothermic reaction, case of an exothermic, A plus B is in equilibrium with C plus D plus heat, putting the reaction in a beaker of water, it's an ice bath, ice and water, you remove heat. That's because you decrease the reaction temperature. When you put a reaction in a beaker of boiling water, otherwise known also as hot water, you increase or add heat. This is adding heat by increasing the reaction temperature. Now, if I look at the clock, we only have a few more minutes left. So instead of going and rushing through a problem, which is not good for you, I know how to do it, but you don't yet, I'm going to hold off until tomorrow. Now, let me remind you of a couple of things. One, I will cut out from this video the answers for quiz 4, but if you need to know them, come to my office hour. If you can't make to my office hour, please email me and we'll see when we can set up a Zoom meeting so we can meet and I can help you out. Also important, because, bad Dr. White, I didn't get out the show you how to do calculations for the airbag lab by 8 p.m. today, hopefully sooner, but by 8 p.m. So I got to teach, and I also have to go to somewhere right after this class for a half hour. It's a busy day for Dr. White, real busy. I will have the calculations in the airbag lab and also email you it so you can do it. And it'll be due not tomorrow, but a week from tomorrow. And with that, I'm done. I'll see you tomorrow. Tomorrow, we're going to do Le Chatelier's principle. And with that, I'll say, Gang gesund. Goodbye. Stole that from Granny and the Beverly Hillbillies.